going to go over very quickly some of the material we just saw kind of in a PowerPoint presentation. First, on descriptive statistics, some of the stuff is going to be a little bit weird because it's going to have some formulas in there that you haven't really been exposed to, some Greek letters and stuff like that. Don't worry about it. We're going to explain. We're going to do some examples of that. You and I both are going to actually practice on some of that stuff. First thing we brought up was the mean, right? So in this format, we're just saying we're taking the sum of all the values, xi, right, from I equals 1 to whatever the total number of people in the study or subjects are, and so on and so forth, and dividing it by n. And we're using the symbol mu, lowercase mu, to mean mean. Okay, anytime we use a Greek letter to represent a statistic, we're talking about a population. Anytime we use an English letter, like an X, for instance, like an X bar, when we sometimes refer to the mean with an X with a bar over the top of it, that's the mean of a sample rather than the mean of the population. So if you see a Greek letter, you know we're talking about the population. Okay. Another measure of central tendency is the median. We talked about the median. Median here is, of course, 20 because it's the middle number. When we all have a middle number, we have an even number of subjects, right? The mean is just the average of the two middle numbers. Okay, so median here would be 35. That's going to come in handy later on when we work with some other stuff that's a little bit more complicated. Okay, just as we did there. Okay. The mode, another measure of central tendency, just the most frequent value. You can see there it's 30. You got a pretty good look at this stuff before. And then we get into something really ugly, the variance and the standard deviation. These formulas describe the calculation, right? This happens to be called the variance, sigma squared, and sigma is the standard deviation. It's going to be easier to actually calculate this than to decipher this formula for the moment. After you looked at this, and some of you, how many of you guys really remember this? Is this something like this a memory for most? So this is a memory for most of you guys, right? Okay, good. I'm glad I heard that because now we're going to calculate this by hand so that there'll be no doubt of what these things, the standard deviation and the variance is. You'll really understand what it is. For the moment, we're going to abandon these formulas. We're not going to look at them, and we're going to actually do calculations in a minute. The other things that are important measures, in this case measures of spread, are the range, which is lowest value to highest value. Remember we talked about interquartile range. There's another, the 25th percentile to the 75th percentile. The variance we just looked at, standard deviation. And then there's other properties of how numbers are distributed. Skewness, we looked at whether, there was a nice normal distribution where it was like bell-shaped and there were equal numbers of people below the mean and above the mean and so on and so forth. A lot of times that's not the case. We see distributions that are leaning towards one side or the other, or skewed towards one side or the other. And we'll get to that in a second. Okay. Percentiles, we'll get to that. Okay, let's see. Okay, of course, it's always nice. One of the reasons we're doing all this, mean, median, standard deviation, variance, is because we want a way to describe to people how the data is distributed. What does the data look like? If I throw 100 numbers up on the screen, it's very hard to understand what's going on with those 100 numbers. But if I tell you where the middle of those numbers, what the mean of those numbers, what the median, at least now you have a measure of what the average value for that entire group of 100 people as 100 subjects is. If I were to tell you what the range was, then now you know the lowest value and the highest value. You have ways of describing this data or this information which are very helpful. It'll help you communicate it. It'll help you understand what it means. In addition to that, we can also display the data graphically, and we already started to work on that. For instance, we started working with histograms. Okay, and here, for instance, we have a histogram which is, I'm going to guess that it's some sort of clinical measurement, right? And it goes from 0 to about 7.5. And this first bar represents all the people, or the frequency of people that have a value between 0.5 and 1.5, or less than 1.5. Because if you were 1.5 exactly, you'd be in the next group. 1.5 to less than 2.5. If you were 2.5, you'd be in the next group. If you were 2.499999, you'd be in this group. So what is this property of histograms that makes it different from bar charts? It's continuous. You're in one group or the other. In other words, it's not like, for instance, a bar chart, male and female, right? There's nothing in between. If we were looking at hair color, it would be brunette, blonde, redhead, green, whatever, whatever colors of hair color that you might have. So there's a difference between a bar chart and a histogram, right? An important difference, right? So there's a bar chart. That's a bar chart. That's a candy bar chart. And I have one more. Wait a minute. That's a sushi bar chart. So there's an important difference. The other way that we can look at data is to see how it's spread out within these groups. Now, one of the things that comes up with some of the automated systems that you use is that a lot of times they'll produce almost routinely stem for SPSS, almost on every calculation produces something called a stem and leaf plot. In this stem and leaf plot, what you have is people that have, one person has a score of 100, another 105, another 105, three people that have scores of 110, and five that have 115. So the way it's organizing this is saying, well, how many people are in that 100 to 110 range? Well, 100, the first two digits, 100, and there's one person with 100, 155, 105, 105. Well, this is 110, 110, 110. And this is another way. If you look at this sideways, it's just a histogram, right, over on its side. So you're going to see every time you use SPSS or some of the other software, it's going to produce these stem and leaf plots, but they're just basically sideways histograms. Okay, now, one of the natures of data that has a random element is that it frequently you'll have the highest frequency around the middle of the data. In other words, if we were to measure weight, right, we'd find that most people that within a certain age group and a certain gender and so on and so forth, they're going to have an average weight. And there's going to be a lot of people that are close to that weight. But now, if we look how many people are going to be 20 pounds under that weight, or 20 pounds over that weight, it's going to be a little bit fewer than might be 10 pounds under. How about 30 pounds over or under? There's going to be fewer people yet. And as we get further and further away, the frequency diminishes dramatically. So it's very common that if we were going to take a population of people and we were going to randomly sample them, you without looking, pick out random people, well, really, half of them are going to be below the average, half of them are going to be above the average. As we select them randomly, well, the people that we select randomly, they're most likely to be close to the average. So we're going to start piling up people in the middle. And then every once in a while we get somebody that's far out above, far out below, but not anywhere as near as frequently as the people that are in the middle. So that, in many cases, is going to wind up creating a distribution which has a common pattern to it, has this bell-shaped curve to it, this normal distribution. Not everything has a normal distribution, but a lot of really important stuff that we want to work with has normal distributions. And normal distributions have common properties that allow us to do calculations that, really enlighten us as to how the data is distributed and whether one set of data is really different from another set of data. So having normal distributions to work with really is helpful for us. Okay. So this is a single mode. This is normal distribution. Typically, it's symmetrical. It's bell-shaped. The mean and the median and the mode are all in exactly the same place. Of course, we can find other situations where it's skewed to the left or the right. It's not perfectly normally distributed. I'll give you an example. Positive skew. Let's say that you guys graduate and you all go out and find jobs, right? And you find that the average salary that the average salary that among all of your graduates is starting salary $65,000 a year. Is that a good salary? That's decent, right? It's not high, it's not great, but it's decent, right? $65,000 a year, right? But then one person gets, winds up with a contract with the NBA, and he's making $25 million a year. Now, if I take it, anybody that tall in here? Probably not, right? Okay, maybe, okay. So he's making $25 million a year. What happens to the mean for the class? The mean is skewed way up. In other words, the mean is pulled way to the right. See that person at the end there skewed the distribution to the right. The median stays in the same place because it's the middle value. It isn't affected by that person that has that really high value. So typically, if you see the mean getting pulled away from the median, in our case, the mean is getting pulled to the right. So that's right skewed or positively skewed. If someone decides they're going to work for a not-for-profit and they're making $5,000 a year, they're skewing it negatively, right? Because they're pulling it down to the other side dramatically. Chevy sections, I don't know if anybody really uses this anymore for anything, but it's in the book, so you have to learn it. Okay, so basically, it tells you that 70%, if you just have any set of numbers, and you have no other way to really deal with it, you don't know if it's a normal distribution or anything like that, 75, you can make the assumption that it's likely that 75% of the values are going to lie within 2 standard deviations in the mean. Of course, we haven't discussed what a standard deviation is. That's going to help if you knew that, right? But we're going to figure that out in a second. 89% of the values are going to lie within 3 standard deviations in the mean. Interesting thing about this is that when we look at a normal distribution, we're actually going to be able to make better prediction than Chevy-Chev in terms of how the population is distributed. Okay, normal, this is for any kind of data. It could be like that bimodal data. It could be, data that's not anywhere near normal and stuff like that. If it's normally distributed, we're going to use the empirical rule, and we're going to use all sorts of other stuff that we're going to be able to use calculations for that are going to be much more helpful than Chevy-Chev's rule. Okay, but this is kind of I guess it was kind of early. I guess an early, I'm not even sure how they derived that, how they found that. Okay, and there's a formula for this. It's I think it's, the percentage is 1 minus 1 over k squared or something like that. That's how you do k represents the number of standard deviations, tells you the percentage. There's actually a couple of problems in the book. I'm going to be posting homework later on tonight. I don't think I picked anything on Chevy-Chev, so beyond today, don't worry about it. They'll never come up again, I don't think. Except maybe you might have to know the name. Okay, then later on we're going to talk about rates, and we're going to talk about certain special rates like death, mortality rates, and we're going to look at other kinds of rates which are have some sort of specific grouping, like age-specific, gender-specific, so on and so forth, and we'll give it a try. Okay, so let me get this out of the way. Okay, let's see. First I want to just show you, let's see if this will play. This is at the New York Hall of Science here in Queens. There's a machine there called a Galton machine. And what it does is it drops little balls on the top here, and those balls come down and they hit like these little bars, and they can randomly go left or right. So you can have a ball that goes left, 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 very rarely, or right, 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 very rarely, or you can have a ball that goes left, half 50-50, left and right, very frequently. And eventually what happens is they accumulate at the bottom, and what do you think they estimate? Right? And remember, this distribution is based on chance. Whether it goes to the left or the right is due to chance. And most of the time, it's going to be about half and half left, half right. And very infrequently, you're going to get situations where it's all lefts and all rights and so on and so forth. That's a special kind of distribution. I kind of cheated a little bit there, but we'll talk about that later on. Okay, so on Blackboard, there is a file. And let's start with number 4, I think it is. Let's open up number 4. And if you download it onto your computer, you're going to be able to do this at the same time that I do it. Okay? So, what I have is a series of, just a little bit of this is a repeat of what we did last week because we calculated the mean, but now we're going to actually figure out what this standard deviation and variance stuff is all about as well. Okay, so now we remember that when we work with Excel. You guys able to download that? You're able to open and download. It's on Blackboard under session 2 under lab, and it's called number 4 Excel Descriptives 1. It's the file there with the number 4 in front. I'll give you a minute to catch up. Let's see if I can't. Where's the Zoom? Bottom right? Ah, okay. Okay, good. I'm going to get the whole thing in there. Okay, got most of you guys caught up with me? Okay, so now, first thing I want to do is here I have some data. It happens to have 11 people in it, right, 11 subjects. And I don't know, maybe this is my group of peers, it's my age groups, maybe these ages or something like that. Or maybe it's like healthy people's blood sugars or something. Okay, so whatever it is, we don't care about that for the moment, but it's a set of numbers. We want to see how we can describe these numbers, how we can understand them. They're not distributed in any particular fashion. It's not sorted or anything like that. So I don't know, to know what the range is, I'd have to kind of mentally find the lowest number and highest number. I have to make a judgment as to where the middle might be, and this might be a little bit difficult. It's difficult with 11 numbers. It's impossible with 1,100 numbers, obviously. So we have tools to do that. First thing I'm going to do is calculate the mean, and I'm going to actually do that from scratch. First thing I'm going to do is take the sum of this column equals SUM parentheses, and I can tell it's the sum of B2 through B12, and hit enter. Oops, what did I do there? Why don't I at least get a couple of things in before? Oh, I misspelled sum. It's hard to work with this keyboard sideways. There we go, 770. Next, I want to know how many subjects that there are, how many values that there are. That's my N. Okay, and I'm going to click in there. And I could just count them. I know there's 11 of them, but there actually is a function in Excel called count. Equals CUCOUNT, parentheses. And I'm going to highlight that same group of cells. Okay, everybody keeping up with me? We doing okay? No? Was that here a no? Okay. Take your time. You okay then? Maybe you could help him out a little bit while we're working on it.
I don't know, I got a name on.
Oh yeah, because he made an error in the formula. Okay, so now if I want to calculate the mean, I'm just going to take the sum. I'm going to put an equal sign in there, take the sum, and divide it by the number of subjects. Okay, which is 11. And the mean is 70. Okay, now we know that if I had wanted to, I could have just put equals average, parentheses, and done the same thing and gotten the same value.
Can you go back to the B15 and just click on that box so I can see what you're putting there?
Which one, the mean?
Yeah.
Yeah, I put in B13 over B14. In other words, a sum divided by the number of subjects. Right? 770 is the sum of all the values divided by 11 subjects. But I put in the location in the cells in case something changes later on. And I did the same thing again in here, except I actually used the function average B2 through B12. Okay, and I found the same value. Okay, well that's great. Now I have an idea of where the middle of this grouping is, where the middle of this data is. It's 70. Now I want to get an idea of how spread out it is. Well, one of the ways that I might describe how spread out it is I might say, well, how far are the individual values from the mean? Okay, so for instance, over here, 70. 70 is exactly the same as the mean. So I'm going to calculate the difference between the mean and that value. That's equal to 70, right, minus 70, okay, which is, 0, right, no difference. Now this cell over here is equal to 75 minus 70, the mean, and the difference is 5. Now, I'm going to redo this. I'm going to go into this cell up here, and I'm going to do a little bit of a trick here. Instead of saying the mean, I'm going to put a dollar sign in front of the B, and a dollar sign in front of the 15. Okay, and I'm going to hit enter. Okay, it hasn't changed the value there, it's still 0. Except this time, I'm going to click in here, and I'm going to drag down to the 71, and I'm going to say, fill down. Is that it? Is that the fill? There it is. That's the fill. Is that fill? Nope. Where is it? It's on the other side. Yeah, on the Mac, it's on the other side. Where is it? Clear, 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 clear. Da, da, da. Where's fill? Okay, come on. It's here somewhere. I know it. Insert, delete, format, cells, fill. There it is. Fill down. Copy the formula down. Why did I put those dollar signs in? Anybody know why I put those dollar signs in? There's something that's called relative addressing, and there's something called absolute addressing. If I click in here, if I copy that formula down into the next cell, since Excel sees this formula, it would have said B2, instead of B2, it would have said B3, minus B, instead of B15, it would have said B16, right? Which is the wrong cell. And then it would have said, okay, the next one, B4 minus B18. It would have kept going down. By putting that dollar sign in there, I told Excel that if I copy this formula down, go ahead and advance the B2, but keep the B15 the same all the time. That's called absolute addressing. That way it doesn't lose the mean. It doesn't go straight down to the bottom of the spreadsheet looking for the mean. Everybody kind of get that idea? Okay. But basically all I did was calculate. You could have, if I wanted to, I could have just calculated 67 minus 70, 67 minus 70, 65 minus 70, 73 minus 70 for each one of these cells individually if I wanted to.
Okay, so to copy the formulas, you need to put in the dollar signs.
In order not to copy the formula, what I did was I clicked in here and I dragged down, right, like that, and I went over here to fill, and I said, whoops, fill down.
Right.
Okay, and I copied the formula from the first cell into the rest of those cells. Okay, the reason why I put those dollar signs in is so that when I went to the second one, see it says, next one says B3, B4. But B15 I wanted to stay the same because I wanted always to be subtracted the mean. That's what the dollar signs do, is they make it an absolute, it says don't advance this. Keep using that same number. Yes?
Okay. Just out of curiosity, why do you put the dollar sign before the B and the?
Because if I only put it before the B, it would keep the same row but keep advancing the number. And if I only put it before the number, it might, if I went across, it would keep advancing the column C, D, but not advance the number. You need both. Absolutely.
Even though you told it so.
Yeah, that's a good question. Maybe it would work. You could give it a try. Maybe you could get away with that, but this will work for sure. Okay, so now the differences. What do you think these differences add up to? Well, I'm subtracting the mean from all the values. What's going to be the sum of all those differences? Half of them are going to be more, half of them are going to be less. Half of them are going to be above the mean, half below, right? 0, right? So my idea of finding the differences and adding them all together, see how big the differences are, that doesn't work because they cancel out because some of them are negative numbers, some of them are positive numbers. Okay, so I need to get this magnitude of differences between all of these values and the mean. I have to get that to be all the same sign. One way to do it is just say absolute values. What's another way to get rid of negative numbers? Square the numbers. Okay, so let's do that. So in here, I'm going to say equals this times itself times itself, that's squared, and then I'm going to copy all these down.
Wait, put that form in, what's there there?
I put in C2 times C2. I just took this times itself. In other words, that's what I'm doing is squaring. You could also use a square function, but it might get complicated. Okay, and I'm going to click in here and drag down again. And I'm going to fill down. Okay, this time they'll cancel out. This time I have actual numbers in there. Okay, 0, 25, 9, 9, 9, 25, so on and so forth. The bigger those numbers are, the bigger the difference is between the values and the mean, which indicates that there's more of a spread. They're a measure of spread. Yes, was there a hand up out there?
So, I was going to say, so the fill down function, it'll know
It'll know to advance.
if you didn't have a fixed number that you wanted to.
Exactly. It'll know to copy the formula down, not the number. If you click first into a formula box and drag it down, it'll know to copy the formula down and to do it relative. Change the row numbers. Exactly. And even though it was 0 in that particular one. And the fill down will do it. If there were a number in there and I did that, just a regular number or a label, even a text. If I did that, it would just copy the text or the number down. Okay, in this case, it copies the number and it does it with relative addressing. It changes the address, but row by row, so it keeps the calculation going correctly. Yes?
And what was the formula again?
I'm sorry?
What was the formula again?
The formula is just C2 minus C2 times C2, right? Just in the first cell. Yes?
I just want to point out that there's like a quick way of filling.
Yes.
You can,
I can never do that with this mouse stuff, because it's crap. Yeah, there's no, So if you click in, there's a little box that appears on the bottom here, and you can actually drag it down, except this mouse is crummy, and I can't do it very easily. So there's a few, anything you do in Excel, there's 97 other ways to do it. There's keyboard shortcuts, there's dragging, there's all sorts of ways to get around this stuff. Okay, so now I'm going to say, okay, well, the bigger these squares are, the bigger the value of all these squared numbers are, the bigger the variance, has more spread out the data is. That's just natural. So I'm going to go into this box here, and I'm going to add up all those squared values. And that adding up of all those squared values is called the sum of squares. Okay, that's the first important statistical function besides mean and median and mode that you've come across. Sum of squares is going to come up a lot in conversation in this course. Right? So the sum of squares is 112. If I had another 11 numbers where the sum of squares was 222, that would indicate a distribution where the numbers are spread out further from the mean. If the sum of squares were 12, it would indicate a distribution where they were closer together. But there's a sum of squares. That's an interesting way to describe the magnitude of the variability, how spread out the data is. Well, now what I'm going to do is I'm going to say, well, that represents the variability for all of those numbers put together. Let's find the variability for the average variability in here, right? Like just when you have average mean, let's find an average variability. Let's take the sum of squares and divide by the total number of numbers there. Now, there's going to be a red herring here in a second. I'm going to put 112 in here, divided by, right? And instead of dividing it by 11, I'm going to divide it by 10, n minus 1. Don't worry about why I'm dividing it by 11. That's called degrees of freedom. Okay, and it really is kind of like an average, except I'm cheating a little bit and I'm subtracting 1 from that. I hate to say this partly because it works better, but there's mathematical reasons for this as well. Okay, but instead of dividing by 11, I'm going to divide by 10, n minus 1. So now I get kind of an average sum of squares, 11.2, right?
I'm sorry.
Yes?
Is that supposed to be the box below it?
Yeah, I'm sorry, n minus 1 should have been, yeah. Okay, if I do this right, I'm going to put 10 over here. And this is going to be equals the sum of squares divided by 10, okay, which is 11.2. Kind of an average sum of squares. That's called a variance. Remember that big formula that we had there? That big formula had a Greek sigma, big Greek, sigma's like a big E, right? Sigma is equal to x minus x bar, the sum of x minus x bar squared, right, divided by n minus 1. That's what was in that formula for variance. That's called the variance. That's how we calculate the variance. Another way for me to calculate the variance is just to say equals variance, I think. I'm about to find out. If I hit parentheses in there and nothing shows up, I know that I didn't get the function right. Variance, VAR. Okay, and if I go back to the original numbers, and I just put in all those numbers in there, and hit enter, I should get the same number, 11.2, and I do. Right? So I could have done that shortcut, but you wouldn't have seen how to get it. Right? You wouldn't have seen how to calculate the variance. That's why we're doing this exercise. Okay, so now the variance is really nice. But the only trouble with the variance is, look at the differences here. The differences are 5, 3, 4, 1, and so on and so forth. They're small relative to the variance. The variance is not very descriptive. It doesn't describe it very accurately what the spread is. The spread is smaller than that variance. Reason why that variance is so big is because what did we do originally with all the differences? We squared them. Well, now, let's bring this back into the order of magnitude of the original numbers. Let's find the square root. Okay, so I'm going to click in here, and it's going to be equal to SQRT, parentheses, square root of the variance. I'm going to hit enter, and that number is 3.34, kind of an average difference. I'll click in there again. It's equal to square roots, SQRT. Remember, you can go into the function menu over here, and if you can't remember these, as I remember, it's convenient for me because I remember, you can click on that function bar, and it'll bring up a table where you can scroll through all the functions and find the ones that you want. They're sorted by, math, statistical, and so on and so forth. So that's the standard deviation. Standard deviation is going to be very important to us. What did we just say about the standard deviation? Where did we just use it? We just used it with our normal distribution, with our empirical formula, and with Chebyshev, right? In other words, now we know that if this is a normal distribution, that 95% of the values are within 2 standard deviations, 2 times 3.3, or about 6.6 of the mean, below and above. That standard deviation is important to us. We're going to use it in a million calculations later on. Okay? For now, we understand now, if we had to calculate from a string of numbers, from data, we know how to calculate the variance and the sum of squares, the variance, and the standard deviation, our basic statistical calculations. Our basic numbers, which we're going to use later on to get a much better understanding of how samples and populations are distributed. In fact, we may play around with a couple now. Yes?
Is it just a coincidence right now that n and the variance are pretty close to each other, or is that?
N and the variance?
Well, the mean is 11, or no, not the mean, the number.
The mean, no, that's strictly coincidence. Absolutely coincidence, yep. Okay, so we know how to calculate standard deviation now. Okay, so now let's take a look at another way of looking how data is spread out. I'm going to take all of these numbers, I'm going to highlight them. And I'm going to say copy. Clipboard. Where is it? Copy. And you can also do Control-C on the PC, or Control or Command-C on the Mac. I'm going to over here to sort, just under sorted, this box over here, and I'm going to say paste. Okay, and pasted those numbers in there. I'm going to leave them highlighted. And now that they're highlighted, I'm going to ask Excel to sort those highlighted numbers for me. And here, you see the rated Z there is sort. If I just click on it, it's going to sort it for me, I think. Sort smallest to largest. Okay, that sounds good. What does it want now? Found data next to your. No, I don't want to do that. It's asking me, do I want to include these numbers over here in the sort? I'm going to say no. Oh yeah, choose the other one. Good idea. Okay. Okay, good. There we go. Okay, so now they're sorted, smallest to biggest. Going to make it a lot easier for us to do the next part of this. Okay, first of all, let's say I want it. What's the range now? The range is 65 to 75. The range is 10, right? Okay, what's the median? What's the mean? The mean we know is from here is 70. What's the median? Well, the median is the middle number. right? There's 5 people below 70, 5 people above 70. That's our median. How about our 25th percentile? Median's is 50th percentile, right? 50% below, 50% above. What's the median for this group? Well, the median is going to be halfway between 0 percentile and 50th percentile. It's going to be the median of this lower group, 70 and lower. So where would the median be there? The median would be, let's see, there's 6 values here. So it would be between 67 and 67, so the median would be 67, right? The 25th percentile would be 67. What would be the 75th percentile? Well, the 75th percentile is going to be halfway between 100% of the values and 50% of the values, and that would, again, since there's an even number, would be an average of these 2 middle numbers, which is going to be 73. Right? So our 25th percentile is 67. Our 75th percentile is 73. Kind of like weird to do this with such a small number set, right? Because 75th percentile, well, there's only 11 numbers here. Kind of weird to call it the 75th percentile. But in real life, you're dealing with much bigger data sets. Like, for instance, all of us here took the GRE recently. Or if we didn't, non-matric, we're going to be taking it soon, right? You have to take it, right? So, when you got your report on your grade on the GRE, it told you what percentile you were. So if you were in, most people in this room probably, 93rd percentile, 98th percentile, right? So you know that you had only 2% that got a better score than you and 98% that got a worse score than you, okay? But sometimes we want to know the middle section. How big is that middle section? Where's that middle section? So a lot of statisticians are interested in something called the interquartile range. And the interquartile range is what values represent between the 25th percentile and the 75th percentile. So in this case, it's 67 to 73. Okay, in the case of a real big data set, it would be calculated a little bit more difficultly. And like if I wanted to calculate this using Excel, I'm going to click in here. Equals median. Now first I'll find the median, since it's going to be handy. We did this before, I think. Parentheses, and I'm just going to highlight all those numbers and then find the middle one for me. Hit enter. Okay, as we expected, 70. Now I'm going to find the lower quartile, the 25th percentile. Okay, I'm going to click in there. It doesn't have a function called quartile. It does have a function called percentile. I'm going to put in here percentile and parentheses, and it asks me, okay, now that you want, I know what you want, percentile, put in that little left bracket, and it comes up, it says, I want to know the array, comma, K. If I went into function, it would tell me what array and K stand for. What array stands for is the set of numbers, the field of numbers that you're working with. Okay, I'm going to click in here, and the field of numbers I'm working with is from there to there. Okay, is G2 through G12. Comma, K represents the percentile. Okay, and that's going to be, in decimal form, it's going to be 0.25. Close parentheses, and hit enter. And the 25th percentile, 67, same thing we got. Okay, I'm going to do the same thing here. For the upper quartile is going to be the 75th percentile. Equal percentile. Parentheses, and again, the array is going to be those numbers. I could have actually gone over to column B and just grabbed them from there too. It doesn't matter, it doesn't need it sorted. We only sorted it to make it easier for most. Comma, and what do I put in here for the percentile? 0.75. Hit enter, and we got the same value we got before, and interquartile range is going to be one subtracted from the other. Whoops. Okay, a lot of basic statistics there. A lot of stuff that you're going to find much easier ways to do, but this is what's really going on behind the scenes. Okay, this is how you calculate variance, that's how you calculate standard deviation, and that's why sum of squares is important, because it's a basic calculation finding all the rest of this stuff. Okay, so I'm going to get rid of this over here, and I'm going to open a data set let me see, which one do I want to open? I'm going to open something simple first. Let's see what 3 looks like. Okay, here's another set of data. I'm actually going to get rid of some stuff. Well, I hate to do this. I'll leave that for you to calculate, you to practice with. Here's another simple one here somewhere. Let's Excel. Something I took here that I simplified. Oh, another complicated one. I had one that I narrowed things down. Maybe I didn't upload it. Or maybe it's uploaded and I didn't put it here. That's more likely.